Good afternoon, students. Welcome to one other lecture in the Advanced Green Manufacturing Systems. We are coming to the close of the course. We have covered most of the topics, and with this lecture, we would probably now cover one of the major concepts that we are trying to do is the optimization and some of the algorithms associated with it. So, without wasting too much of time, I'll just jump into today's topic. So, if you look at today's presentation, we have overview of optimization methods is what we are going to do. We've seen how the optimization problems are, and now we are trying to look into what are some of the methods, how do we solve this. And today's learning agenda, we look into something called total enumeration and branch and bound search, then improving search heuristics, which is called as local search, and the extensions of local search. These are the four concepts that we will cover today. So, first let us talk about this new concept that we are going to cover today in the class. So, what have we learned so far? What did we learn on optimization so far? What did we do? The thing that we learned so far is how to formulate an optimization problem. How to formulate an optimization problem. This we have seen. We are good at identifying how are we formulating this. Okay, this we know how do we do that and what are the other aspects of it. We have a good idea. Then we also saw how to use software to solve optimization problem. Okay. Here in this case, we have been limited to what we call as continuous variables. Okay. So, our variables are continuous in nature, continuous variables, that means they are vary from x varies from minus infinity to plus infinity. Okay. This is what our concept was, and we know how to formulate those problems, and we learn how to solve them using software packages, right. The trick is that many situations will happen where many situations will occur where variable values, the values of the variable values are not continuous. Okay. These variables are not continuous, or in other way only discrete values are possible. Okay. So, what we are saying is that many situations, many of the optimization problems will not have the variables as continuous variables. Instead, only discrete values are possible. Discrete means integer values, countable values, those kind of things. Okay. So, for the linear programming problem, or what we call as LP, okay, where the variables are continuous and stuff like that. Okay. Few prominent algorithms are sufficient to handle vast majority of the models of the optimization models or optimization problem. So, for LP problems where the variables are continuous, there are few algorithms available, they are prominent algorithms, and they are sufficient, they are very good in handling majority of these models. Okay. But the major important thing for us is, but discrete optimization problems, what are discrete optimization problems? Variables are not continuous, okay. Your variables are not taking a continuous value. Okay. These discrete optimization problems often require clever methods that are specialized for individual scenario. Okay. So, for each individual scenario, okay, specific scenario of the discrete optimization problem, we require clever methods that are specialized. Highly specialized clever methods are required for discrete optimization problems. The reason being is variables are not continuous. So, hence LP like algorithms not possible, we cannot use those algorithms to handle such kind of problems. Okay. So, what are some of the commonly used methods? Our question today is, this is what we are going to learn today. What are some of the commonly used methods? On which context? For discrete optimization problems. And this is very common because in real life, in manufacturing, you do discrete manufacturing most of the time. You make cars, you make parts, you make engines, all those kind of things. They are all discrete optimization problems because they are countably discrete. There is no continuous values there. Okay. So, the first and foremost algorithm that we are going to talk about is total enumeration. And you would not believe this is a pretty effective thing for small cased problems. Okay. So, like one of the things is, it is often counterintuitive. It is often counterintuitive that discrete optimization problems. What are discrete optimization problems? Problems where the decision variables are not continuous. Problems are more difficult than their continuous analogues. So, what we are saying is that the discrete optimization problem for a particular case is more difficult to solve than the same continuous analog or the analog problem, which is where the variables are in continuous. Why? Because it appears that only a finite number of choices are possible for decision variables. A finite number of choices are possible for decision variables, hence should be easy. So, you think that in a continuous problem, the variable can take infinite number of choices, okay, any value it is possible, whereas in a discrete problem, there are only limited values, a finite number of values are possible for the decision variables. Hence, it should be ideally easy, but it is actually counterintuitive because it is not easy. Because when the variables are continuous, the most easiest thing is that you can use things like mathematical things like differentiation, integration or slope, those kind of things, gradient like techniques. Whereas in these kind of problems, that kind of a thing is not possible. Okay. So, let us say one hypothesis. Hypothesis 1. Let us think about an important hypothesis in this regard. If a model, okay, that is a discrete optimization. Okay, discrete optimization model has only a few discrete decision variables, if a model has only few discrete decision variables, the most effective way or effective method of analysis is enumerate all possibilities to obtain optimal solution. Okay. So, what we are saying here is, if the problem, the model is a discrete optimization model and there are only few decision variables, okay, number of decision variables are very small, then the effective way of getting the optimal solution, how can you find the optimal solution effectively, is to enumerate all possibilities, okay, run through all possibility options and then find out. Okay. This method, this approach is known as total enumeration. So, when somebody says total enumeration, then you should understand few things. One means the decision variables have only few discrete options, and then out of this you are able to get an optimal solution. Okay. So, this total enumeration, where we define it as checking of all possibilities. Okay. You are checking of all possibilities implied by discrete variable values. Okay, or taken by discrete variable values are conducted. You do all discrete variable values, you take them and you check all those possible values, and then choosing the best combination, that gives the best objective value, that gives the best objective function value. So, what you are trying to do here is, you check all possibilities implied by the discrete variable, whatever the decision variables. Okay. Remember, these are very few in number. Okay. These few discrete decision variables, you find out what are the all possibilities values it can take. Then what you do is, you choose the best combination of this, that gives the best objective function value. Whatever is the best combination, you take that and you call it as the best objective function value. That is the idea. Okay. Fine. So, let us see a simple example. Okay. Let us look at a example of a total enumeration. Okay. So, this is kind of like a tricky problem, but I think it will make. So, let us write a linear programming problem, maximize, that is objective function, 7x plus 4y plus 19z, okay, and subject to the constraints is x plus z is less than or equal to 1, then y plus z is less than or equal to 1, then x, y and z, they are element of 0, 1. Okay. So, what you are saying is that your three variables, okay, these are the coefficients of the variables, that is this is the objective function, okay, objective function, and these are your constraints, right. So, then obviously the thing is that the most important thing that you should understand is x and x, y, z, okay, the decision variables, okay, the variables on which you can take decisions x, y and z, okay, can have either 0 or 1 as its values. So, you can have only either 0 or 1 in this particular case for the decision variables x, y and z. Okay. So, since there are three variables, how many possibilities are there? Three variables, each having two values possible, which gives you 2 to the power of 3, 8 options, 8 possible choices. So, 8 possible choices, this is manageable by you. So, what are the possible choices? Okay, let us say the possible choices. Okay, the possible choices in our case are let us call it as of x comma y comma z is the possible choice. If you say 0 0 0, that is one possible choice. So, that means all the values are 0. Then the other possible choice is 0 0 1. Okay. So, x z taking value of 1. Third choice is 0 1 0, where y is taking this one. Then you can have is 1 0 0, that is another possible combination. So, each one of them taking this particular value. Then we can have another value as the 0 1 and 1, where both y and z are taking the values of 1. So, it is 2 4 and 5. So, then the other value that is possible is 1 0 1, x and c taking 1 and y taking 0. Then the other value that is possible is 1 1 and 0, right. And so, now you have 2 4 6 7, and the last possible value is all taking 1, right. Now, let us see in these cases, okay, what are the values of the objective function, right. So, now let us say constraints. Okay. So, let us see if you put the value of 0 and 0. Okay. So, let us see the first constraint, okay, the two constraints, right. So, this satisfies the x, y and z, these variables element of 0 1. This is satisfied in all cases. Okay. So, then the other constraint, okay, which let us call this as constraint 1 and let us call this as constraint 2, right. So, the x plus z less than or equal to 1, okay, is it satisfied in all cases? So, this is x, y and z. So, this is x plus z less than or equal to 0. So, 1 2, okay. So, 1 is satisfied. So, we have put 1 2. There is also first constraint, second constraint, first constraint, second constraint, first constraint, second constraint, first, second, first, second. So, there are two cases in this regard. So, the case of constraint 1, okay, check which all satisfy. So, we check the first constraint, which one of them x plus z less than or equal to 1, is that satisfying. So, 0 plus 0 less than or equal to 1, that is correct. This case is x plus z, so 0 plus 1 less than or equal to, this is also satisfied. This is 0 plus 0 less than or equal to 1, satisfied. 1 plus 0 less than or equal to 1, satisfied. This is 0 plus 1 less than or equal to 1, satisfied again. This is 1 plus 1, that is 2 less than or equal to 1, not satisfied. 1 plus 0 less than or equal to 1, satisfied. 1 plus 1 less than or equal to not satisfied. So, these two cases immediately you can say that okay fine, I do not need to deal with this because this is infeasible on 1. The first constraint is infeasible. Here is also infeasible on 1. So, with the first constraint we know that these two are not needed. So, then we do not need to check the second constraint at all because you can, this problem you can eliminate. So, now immediately from 8 you are now reduced to 6 of them. Now, let us look at the second constraint which says y plus z less than or equal to 1. This is the check which all satisfy. So, now we are checking which all will satisfy. Y plus z less than or equal to 1. So, y plus z less than or equal to 1, 0 less than or equal to 1, this satisfies. Y plus c, so 0 plus 1 is 1, 1 less than or equal to 1 satisfies. 1 plus 0 less than or equal to 1 satisfies. 0 plus 0 less than or equal to 1 satisfies, right. And then 1 plus 1, this is less than 2 less than or equal to 1 does not satisfy, right. Then in this case 1 plus 0 less than or equal to 1 satisfies. So, we get this particular case also infeasible on 2. Okay. So, of these cases we know that we do not need to worry about this case, we do not need to worry about this particular case, and we do not need to worry about this particular case. So, out of 8, 1, 2, 3, 4, 5, these are the 5 possible cases we just need to now check. So, our possible cases in this include. Okay. So, now if you continue with this working of this example, the possible cases are now the evaluation cases. The cases that we need to evaluate in this case include 0, 0, 0, okay. Then we have is 0, 0, 1, then we have is 0, 1, 0, then the next one we have is 1, 0, 0, and we have is 1, 1, 0. So, these are the 5 cases. If you look into this, we got these values from this particular table. So, we are only evaluating these cases. Okay. So, now how do we evaluate that? So, now we do is this, we just need to find the objective function value, okay, because these are feasible, these conditions of them are feasible, we already checked the feasible. Now, we just need to find what the objective function value is. So, how do we calculate? The calculations include like this. So, for 0, 0, 0, it is equal to 7 times 0 plus 4 times 0 plus 19 times 0, which will give you 0. So, the objective function value is 0 in this case. Okay. The other case is, let us take 0, 0, 1, then it will be 7 times 0 plus 4 times 0 plus 19 times 1, that will be 19. So, 0, 0, 1 will give you the value of 19, right. Then you have 0, 1, 0, 0, 1, 0 will be 7 times 0 plus 4 times 1 plus 19 times 0 will give you 4. Okay. So, 0, 1, 0, the objective function value is 4. Now, 1, 0, 0 will give you 7 times 1 plus 4 times 0 plus 19 times 0 will give you 7. So, this value is 7, right. Now, the last one is 1, 1, 0. So, that will be 7 times 1 plus 4 times 1 plus 19 times 0 is 7 plus 4, 11. So, that objective function value is 11. So, these are the 4 possible objective function values. Now, the objective was to maximize. Okay. Since the objective was to maximize, choose the largest value of objective function. Okay. So, what you are doing is, from here this is the largest value of objective function. So, we say this is the best possible solution for this. Okay. So, the solution is that, so what we are saying that the value of x is equal to 0, value of y is equal to 0, value of z is equal to 1, okay. Objective function is 19, okay, and this is the best possible setup for, this is the optimal solution for the problem. Okay. So, depending on the constraints, we have already seen that we eliminated infeasible solutions. Okay. These are all infeasible. So, we eliminated them using both constraints, and then only the remaining ones were worked out to find out what the best possible solution is. Okay. So, this where we, so we evaluated limited and yet feasible alternatives of decision variables. Okay. So, we evaluated and yet feasible, and yet all feasible alternatives or decision variables were done, and hence this is why it is called as total enumeration. Okay. Hopefully, this makes sense to you. From there, we get into the next algorithm or next approach, what we call as branch and bound search. Okay. This is also a very popular approach among a lot of people, and let us see what it is. Okay. What is the major drawback of total enumeration? Major drawback of total enumeration. What happens when you do the total enumeration? What is the major drawback? Why is it like people don't heavily use it? Okay, this is not feasible for a large set of decision variables. Okay. So, if you have a large set of decision variables, this is not very feasible. Why? The exponential growth of solution space of solutions. Okay. So, for example, if 3 decision variables, okay, let us say 0 1, then it is 2 to the power of 3 8. Let us say if 4 decision variables, again 0 1, then it is 2 to the power of 4. What is that? 2 to the power of 4 will be 16. Okay. So, now if it becomes 5, then it will be 16 times 2, 32. So, it will grow. So, this solution space will grow something like this. Okay. This exponential growth, if this is the number of decision variables. Okay. This is the solutions. If you draw a graph like this, then the growth will be like an exponential growth. So, then when it is large number of decision variables, now you have to look at, if there are 5, then you will look at 32 options. Pretty soon it becomes manually impossible for you to evaluate the things. Okay. So, then alternative, what else can we do? Okay. What is alternative to this headache? Okay. So, this is the, let us say, hypothesis 2. Okay. The second belief system, that if we have a way to deal with problems having large set of decision variables, okay, if we have a problem which has large set of decision variables, okay, can the optimal solution be found without enumerating, without explicit enumeration of all possible unfeasible cases. So, what we are trying to say, or our belief is that if there is a way, if there is a method available where problems having large set of decision variables are there, they are all discrete decision variables, okay, where we still want to find the optimal solution. We want to get the optimal solution that is provably optimal, while we do not want to enumerate all possible and feasible cases. Okay. So, then branch and bound, okay, is one such strategy. So, we call it as it is a subset enumeration strategy. Okay. So, we are saying is that we do not want to enumerate every possible options. Okay. So, what we say is that systematically form classes of solution, systematically form class solutions and investigate whether the classes can contain optimal solutions. So, what you are saying is, from the total problem, you create systematically from the classes of solution and see whether these classes can contain optimal solution. If you find that the classes cannot contain optimal solutions, then don't look into that class. If you find that the class can have the optimal solution, then look into this. Okay. So, that kind of an approach. So, usually the tree search approach is used to expand options. Okay. So, or classes. Okay. So, what we do is we use the tree search approach in this regard to see whether we can actually systematically form the classes of solution and then investigate whether the class can contain the feasible solution or not. Okay. So, again as I said earlier, let us look at a simple example of this one. This would make you understand the problem better. Okay. So, this is a single machine scheduling. Okay. So, the idea is that you have a machine, a single machine. Okay. Let us call it as drill, and entities arrive. So, they arrive into the system. Okay. This is at the queue or something, and then they get drilled here. Okay. Then there is a processing time P I j, okay, or whatever the processing time, and then they leave. Okay. And this is the machine. Okay. So, what happens is there are, like say, and jobs arrive. There are different jobs that are available. So, let us call the number of jobs for this case as 1, 2, 3 and 4. There are 4 jobs available. The processing time, okay, P I. For 1, let us make the processing time as 37. For 2, the processing time is 27. 3, the processing time is 1, and the 4, the processing time is 28. Okay. And then there is one more that is called as due date, okay, where you are supposed to deliver the. So, this is the processing time, this is associated with this. Then here is a customer sitting here, and here is the delivery. Okay. And this is where the due date happens. Due date means when you have to give it to the customer. So, in this case, let us put a value of 49, let us put 36, let us put 1 and 37. Now, the question here is, okay, so we can schedule it in many ways, but find the schedule that minimizes lateness of all jobs. Okay. So, what you are trying to do is we want to find the production schedule that minimizes, or find the sequence, okay, or schedule, let us call it as a sequence for the time being. Schedule and sequence, there is only much small difference. So, sequence means there are 4 jobs. Okay. So, there is Roman numerals are sequence positions. Okay. These are sequence positions, and we have to decide which job will go into which sequence position in this regard, right. So, you can solve it as a discrete optimization problem as well, or you can use branch and bound to solve the case. So, one way to think about this problem is that, ideally speaking, you can think about it as a tree search. So, if you say you call this as 0, let us call this as root node, okay, for the time being, and let us call this as the position 1, okay, position 1. So, then you can have 4 possible options out of this. You can put 4 possible jobs. Okay. So, these are the 4 possible jobs. So, if you put 1 here, 2 here, 3 here and 4 here. So, that is equivalent to saying sequence position 1 is taken by 1, 2, 3 and 4. Okay. Then we take from here, once you fix this, when you say I am going to come to this particular portion, then you can say that there is another position called position 2, the sequence position 2. In that position 2, in this job you can have 3 underneath them. Okay. So, once 1 is fixed, then you can have for the position it is 2, 3 and 4. Any one of them can take the sequence position 2. For 2, again there is possibility of 3. Okay. So, this is 1, 3 and 4. You can't use 2 because 2 is already gone into the first sequence position, right. So, then if you think about this, below that you have something called as position 3, the sequence position 3, there are only 2 possible options for this case. Because you already used 1, you already used 2, then the possibilities are 3 and 4. So, then the last case is position 4, this can have only 1, it can be 4, this can be 3. So, when you think about this sequence becomes 1, 2, 3, 4 and the other sequence is 1, 2, 4, 3. So, what you have done is, this is where you have created something called as a, what I mentioned earlier, this particular term is systematically formed classes of solution. Okay. Systematic class of solution forming. That is what we are doing here in this particular case. So, how would this actually help us in solving the problem? So, let us see an example. Okay. This same example, let us work out a little bit longer. So, that would probably help us in understanding the mechanics of the problem. So, our root node is 0, okay, and we have our 4 sequence positions. Okay. I hope we get space here, 1, 2, 3 and 4. Okay. So, the first sequence position is taken care of. In this case, we have made the first sequence position set up to 1, 2, 3 and 4. Now, you can decide the minute you put 1 here, okay, the time taken to produce, okay, the PI for, so the lateness, let's call lateness equal to due date di, the job, minus sum of PIs, all the processing times. So, for this case the lateness is equal to, what is the value of lateness? The due date, the processing times are 37, 27, I am just writing it here for the time being, making my life easy, 1 and 28. Okay. So, for 37, if you think about it, the due date of this problem is, I am writing the due date on this side, which is 49, okay. This is 36, then this is 1 and 37. Okay. So, in this case the lateness is 0, in this case also the lateness is also 0. Okay. I am just putting L equal to 0 here. This is also lateness equal to 0, lateness equal to 0. Okay. Fine. Now, there are multiple ways you can think about. Okay. So, sometimes what people do is, okay, fine, I will take one of these subclass and expand it, and so that I get a solution out of it, and see wherever I exceed this, I do not continue this problem. So, let us look at that example. So, I am just going to take this branch 1 and expand out of it, right. So, the next one I am going to do is, okay, the sequence position 1. So, you finished that. So, now let us think about the next job that we are going to put in here. We have 3 jobs here possible. Okay. That is 2, 3 and 4, okay, for us. So, now the processing time of job 1 is 37. If we put 2 here, okay, so then that becomes the time, the 2's processing time is, which is 2's processing time is 27. So, the time taken is, the Pi, sigma Pi in this regard is, here will be, I will kind of use the bottom portion, the sigma Pi is equal to 37 plus 27, right. So, that will give you 7 plus 7 is 14, 3 plus 2 5 plus 1 6. So, this will be 64, okay, 64, and 2 is supposed to be delivered on 36th day, okay, and you are already late now. Okay. Now, about 3, if you think about it, 3 the time is 1. So, the sigma Pi for 3 will be 37 plus 1, that is 38, right. So, this will be 38, and 3 is supposed to be delivered on day 1. So, you are already late, okay, again. And if you think about 4, it will be sigma Pi will be is equal to 37 plus what you call as 4 will be 28, okay. So, that will be 65, okay, 65, and 4 was supposed to be delivered on 37th day. So, you are late here. So, by the second sequence position itself, your solution is not very good. You are already late big time, right. Now, same way if you can think about it is, so some people will say, okay, fine, then there is no point in going here. Let me see whether there is any other scenario where it is better. So, you can try the next one, the second one, and let us see for an example. I take the second sequence position. I have 3 jobs possible here. So, I put it as 1, 3 and 4, and if you think about it, the time taken for this is 27. So, the sigma pi for the first branch is, it is 27 plus 1 is 37. So, that will be 64. The time to deliver is 36, it is late. Okay. So, then 3 will be, it is 27 and 3 is time is 1. So, 28, and it has to be 3 has to be delivered in due date on 1, it is still late. 27 plus 4, so that will be 4 is 28. So, this case will be sigma pi will be 27 plus 28. So, that is 15, 2 plus 2 for 5, 55. So, in this case it is 55 and it is supposed to be delivered on 37, it is still late. So, you are like, okay, fine, here also by the second sequence position everybody is late. Okay. So, now let us look at the third one. We can say is that, okay, there are 3 places that we can do at this point. So, 1, 2 and 3. Okay. So, I can put 1, 2, 4. Okay. So, these are the 3 options I have, and this one, if you think about this, 3, the number of the processing time is 1. So, there is no lateness here, and so then the next job is 1 we are taken, and that is 37, right. So, 37 plus 1 is 38, and it is supposed to be delivered on 49. So, no lateness, L is equal to 0. If I do 2, then 2 will be 1 plus 27, that is 28. It is supposed to be delivered on 36. The lateness is equal to 0, and 4 is 28. So, that is 29. Okay. So, then the due date is to be 37. So, the lateness is equal to 0. So, now here is a scenario where the second sequence position none of the jobs are late. So, which means now this is compared to these 3 cases, I can say that this is a promising subclass. So, compared to these guys, these two one, this subclass, the first subclass and the second subclass, this subclass is better because here all the jobs are late by the second sequence position, and here none of the jobs are late by the second sequence position. So, then I can do is from here I can expand the third sequence position then. So, in this case it will be 2 sequence positions will be used in this case, that will be, I am just going to expand it for the time being, okay, just to expand. So, this will be 3 and 1 are used. So, it will be 2 and 4 are the 2 possible options in this case, right. So, then if it is 2, so this is 38 was the total processing time so far. So, the sigma pi for us is 38, and for 2 the time is 27. So, 38 plus 27. So, it is 8 plus 8 16. So, it is 5, 3 plus 2 is 5 plus 1 6. So, this is 65, and 2 is supposed to be delivered by 36. So, you are late here, okay. And then with 4 you can find out 4 is 28. So, sigma pi is equal to 38 plus 28. So, 16 and 3 plus, so 3 plus 2 is 5, 5 plus 1 is 6. So, it is 66, okay, and 4 is to be delivered at the time of 37. So, this is late. Okay. So, both the jobs are late in the sequence position. So, now if you look at the next ones, then you can say that this 3 2. So, the next option is you have is 1 and 4. Okay. So, these 2 guys will have that, and then you expand it, and then in this 4 case you will have 1 and 2, okay, right, like this. And then from here then you calculate which is the lowest lateness, and then from there you can decide which lateness or so far, you might be promising and continuing that. And then wherever you find a lateness more. So, this process what we are doing below, okay, this is called branching, expanding the solution to the branches of the trees is what we call as the branching. And then let us say for example, I just let me take one example in this case. I have already let us say 28 is here, and then with 1 the it is 37. So, let us take one example is that here this is let us say 4 and I got that is 65. So, sigma p I in our case is 65 plus the processing time of 4 is 28. So, 28 that, so it is 93. So, let us say get the total processing time as 93, and let us say the sum of the lateness in this particular case is, let us say you get a value of let us say for example take it as 30. Okay. So, the L value is 30. So, let us say you get the for this particular branch, let us say for the L value here is 31. Then what happens is, you know that going below this branch is not going to help, okay, because it is not going to get you any better solution. So, do not enumerate, okay, called bounding. Okay. You are terminating or stopping or cutting the search. Okay. So, there is other thing also is called bound. So, I would not call it as bounding, I will call it as pruning. Okay. What I am using is, I am using this as the bound. Okay. So, I am saying that with this bound, this L equal to 30 whatever I calculated, I can basically stop all those branches of trees. I can stop all those enumerations where I say, look, there is no need, I do not need to expand this because my solution is not going to be better. So, using the bound. So, why do you use bound? Bounds are used to reduce the number of leaves. These are the leaves, okay, leaves evaluated in a tree. Okay. So, this approach what I am just talking to you as of now is what we call as a branch and bound algorithm. Okay. You branch on different branches like you branching on a tree, okay, and then you use a bound to ensure that you do not evaluate all possible options in this particular example. So, I hope you understand how I am how this method works. There are different implementations of these methods by different people, the different variations of this also, but the fundamental idea is somewhat like this. Okay. Fine. So, now we get into the last possible options which is called as the heuristics and optimization. So, the heuristics and optimization is also another important aspect that we need to consider in this case. Okay. So, one of the main things that you need to understand is most of the large scale optimization problem, most of the large scale optimization problems settle for some kind of approximate optimization. You are trying to look for some approximation which we typically called as heuristic, okay, some approximate optimization method to obtain feasible and good solution. Okay. Some people also call, but not necessarily optimal solution. Okay. So, what you are trying while managing the computational effect. computational effort. Okay. So, what you are trying to say is that why when you are looking at a large scale optimization problem, so then you set for some you try to tend to use more of an approximate optimization or a heuristic method for getting feasible and good solutions. Your aim is to obtain feasible and good solutions. So, when you do that, what you are trying to do is you are sacrificing, you are okay with the scenario where you are not going to get an optimal solution, but the computational effort can be managed. So, that is the idea in this one. So, the one thing that you need to learn about this point is called constructive heuristics. Okay. So, constructive heuristics is that aims to build an approximate optimum incrementally. So, step by step you make an approximate optimum. Okay. An approximate optimum is created one step at a time. Okay. So, how do you do? Values for discrete decision variables are chosen one by one. So, you choose these variable values one by one, okay, chosen one by one. The discrete decision variable values are chosen one by one, okay, and stopping when a full feasible solution is obtained. Okay. As long as you have a full feasible solution and as soon as you get it, you stop it. Okay. Many times, many algorithms, many times stopping happens upon obtaining first feasible solution. Okay. So, many times as soon as you get your first feasible solution, then you stop. Okay. Sometimes it can happen in single pass and then some people call it as single pass, one pass heuristics and those kind of stuff. Okay. So, there are many names and other terminologies used in this particular scenario, but the idea is that you basically choose the values of discrete decision variables, you choose them one by one and stop it when as soon as you get a full feasible solution, right. All right. So, this method of this approach is called as a optimization and heuristics in this, or how do you use heuristics for optimization. We will actually see a simple algorithm and probably see an example soon. Thank you.